Hi guys, welcome back to Worms Maths Academy. It's been a while, but sorry I've been busy, but let's get back into it. So I've just gone previously, the last topic was fogs and goffs or composite functions. So now we're going to look at inverse functions. A lot of kids, generally they ask me, can you go through some harder style questions? So I've chucked on a recent exam question, which was pretty hard. I consider it pretty hardest in terms of, what exam one questions are like, but we'll have a look now and you can decide for yourself. Okay, so an inverse function is the opposite relation, I guess you would say. So if I cube something like the number 2, I get 8, which means if I cube root 8, I get 2. So cubing something, its inverse function is the cube root. If I had squared, the inverse would be square root. If I had sine, the inverse would be sine inverse. So our inverse is basically our opposite function. Okay, so one basically negates the other. So a function f will have an inverse function, f negative 1 of x, that's f inverse of x, that's what that means. F inverse of x. If and only f is a one-to-one function. So we've done functions earlier. If it's a one-to-one function, it's got to pass the vertical and the horizontal line test. The rule for finding the inverse is found by interchanging x and y in the equation, transposing to make y the subject. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. Because we swap x and y values, our domain and range switch. So they swap. Okay, inverses are a reflection in the line y equals x. So if I had a graph that was like that, if we sketch the line y equals x, its inverse is just a mirror image in the line y equals x. Sometimes a domain will be restricted, so you need to restrict a domain to make it one-to-one. So here, if we've got x squared, it's not one-to-one, it's a function, but it's not one-to-one because it passes through twice. However, if I restrict the domain to be greater than or equal to 0, it's now a one-to-one function. Okay, so sometimes you have to restrict a function to be one-to-one. I could have also taken the left-hand side of that graph. So I didn't have to take the right-hand side. I could use the left-hand side, but in this case, we just took the right-hand side. Okay, so I guess with a parabola, the main thing you need to know is the turning point of the graph, because that's where you restrict it to be one-to-one. So if I wanted to graph this graph, I could just graph it. But first thing I want to do is put it into turning point form, which makes it easier to graph it. So f of x is equal to x squared minus 4x. If I halve 4 and square it, half of 4 is 2, squared is 4. I've got to add 4 on to make it a perfect square, which means I've got to subtract 4 because I don't want to change the equation. And then we've got plus 8. So we can say that this is x minus 2. It's always a half of that value, all squared. So this thing here and this thing here are exactly the same, and now we've made it a perfect square. Okay, and then we've got plus 4. So this graph, we know it's been moved 2 to the right and up 4. So if I go 2 to the right, 2 to the right, and then up 4, 2, I haven't stuffed that enough, have I? That looks good. Okay, so if we let x equal 3, we're going to get 1 plus 4 is 5. So we get 3, 5. If we let x equal 4, we're going to get 4 plus 4, which is 8. So we're going to put 4 and then 8, so my graph is going to look like that. So we've got 2, 4, we've got 1, 5, and we've got 1, 5, can't be 1, 5, 3, 5, and then we've got 4, 8. Okay, now without actually finding my inverse function, I could sketch it because we know we're swapping x and y. So if I've got 2, 4, that can become 4, 2. If I've got 3, 5, that'll become 5, 3. If I've got 4, 8, that'll become 8, 4. So it'll look something like that. Where are we? 4, 2, 5, 3, 8, 4. And as you can see, here is the line y equals x. You can see that they're the mirror image of each other. And this line has a domain, x is greater than or equal to 2, and it has a range, y is greater than or equal to 4. This one here, x is greater than or equal to 4, y is greater than or equal to 2. You can see their domains and their ranges have swapped. Okay, so let's use this to find out what the inverse function. So you can say let y equal f of x, swap x and y. So if we swap x and y, we get x is equal to y minus 2 squared plus 4. We get y minus 2 squared is equal to x minus 4. Y minus 2 is equal to plus or minus the square root of x minus 4. Now, because we've taken the right-hand side of the graph, when we get the square root graph, we want to take the top half. If, I'll just show you this and then I'll get rid of it. If we had taken the left-hand side of the graph, we'd have needed to take the bottom half to be its inverse. So we'd have used negative x. But in this case here, we want to, so I'll say need top half of graph. So therefore, y is equal to root x minus 4 plus 2. Now we know this is the inverse, so you have to state f minus 1 of x is equal to root x minus 4 plus 2. And we should state the domain when we create a function. So we know the range of the original function's y is greater than or equal to 4. So the domain of this is x is greater than or equal to 4. And we've sketched both of our graphs. We didn't actually have to find the function to do it, but we need to anyway. Okay, a lot of people would struggle with this one to start off just because I don't know where to start, but it says to put it in that form. So we've got, well, there's two ways you can do this. You can do x minus 1 into x plus 1. X's into x goes once. Multiply it back out, we get x minus 1. When we subtract, x minus x is not 0. So nothing. I should just leave it as nothing. 1 minus minus 1 is 2. So we can say that x plus 1 on x minus 1 is equal to 1 with a remainder of 2 on x minus 1. So that's in that form, which we wanted. So that's using long division. Here's another trick way. And sometimes it doesn't work very well. So x plus 1 on x minus 1. So if I wanted to make the top x minus 1, if I didn't want to change the top, I'm going to put a plus 2 because x minus 1 plus 2 is just x plus 1. I haven't changed anything. Then on the bottom, I've got x minus 1. We know that x minus 1 on x minus 1 is 1. Plus, we've got a 2 on x minus 1. So that's our remainder on x minus 1. Probably the best thing, if you struggle with maths especially, you should just do the long division way. So x minus 1 into x plus 1. X is into x goes 1. X minus 1. When we subtract, we end up with 2. So therefore we say y equals 1 plus 2 on x minus 1. Now we've got to sketch this graph. So it's a hyperbola. It's been translated one right. So we need to say x is equal to 1. It's also been translated one up. So y is equal to 1. Now if we sketch it, if we let x equal 0, we get y is equal to 1 plus 2 on negative 1 minus 2. So it's minus 1. So 0 minus 1. If we let y equal 0, we get negative 1 is 2 on x minus 1. If we switch these two things, we get x minus 1 is negative 2. X is negative 1. So a graph's going to look like that. If I put 2 into it on the bottom, if we let x equal 2, 1 plus 2 on 1 is 3. So 2, 3. So that's going to look like that. Now the strange thing about this graph is if I find its inverse, if you have a look here, what can you see is going to happen? So I'll rub this out. So for its inverse, we'll say let y equal f of x, swap x and y. So therefore, now we know that this was y equals 1 plus 2 on x minus 1. So we get x equals 1 plus 2 on y minus 1. X minus 1 is equal to 2 on y minus 1. Switch these two. Y minus 1 is 2 on x minus 1. Bring your 1 to the other side. Y equals 2 on x minus 1 plus 1. You can see they're exactly the same equation. So therefore, f inverse of x is equal to 2 on x minus 1 plus 1. My domain and range, well, we know our domain, x is an element of all reals, except for 1, because that's the range of the original function. And we know our range is all reals, except for 1, because that's our domain of our original function. And if we were to graph it, our original graph and our inverse graph are exactly the same. That's because when you reflect that graph from the line y equals x, it's exactly the same graph. Okay, so to find an inverse graph, we swap our x and y. The function needs to be 1 to 1 before. All hyperbolas are 1 to 1, so we could just go on and find the inverse graph. Use long division to make that prettier, I guess you would say, and then go from there. Okay, now here's that hard question I was talking about. It says the rule for the function f is given by f of x equals 2x plus 3 minus 1, where f is defined on the maximal domain. So here, if I wanted to find my maximal domain, we know that 2x plus 3 has to be greater than or equal to 0. So x has to be greater than or equal to negative 3 on 2. Okay, and my range, well, if this bit equals 0, then my y values are greater than or equal to negative 1. So that's my domain and range. Find the domain and the rule for the inverse function. So we'll say let f of x equal, or I should say it the other way around. Let y equal f of x. Swap x and y. So therefore, x equals 2y plus 3 minus 1. Bring our 1 to the other side, so we get root 2y plus 3 is equal to x plus 1. 2y plus 3 is x plus 1 squared. So I've got 2y plus 3 equals x plus 1 squared. 2y is equal to x plus 1 squared minus 3. So y is equal to 1/2 x plus 1 squared minus 3 on 2. Lastly, we state f minus 1 of x is 1/2 x plus 1 squared minus 3 on 2. Now it says find the domain, so it's going to be our range of this function. So our domain is x is greater than or equal to -1. Now don't forget, this is a square root graph, so it's been moved -3 on 2. Let's make it easier. -3 on 2, and it's been moved down 1, and then it goes like that. Okay, so if I found my original function and my inverse function, they're going to intersect on the line y equals x. So instead of letting my inverse function and my original function be equal to each other, what we can do is say let f of x equal x, because we know that they would intersect on the line y equals x. So we get 2x plus 3 square rooted minus 1 is equal to x. 2x plus 3 is equal to x plus 1. Square both sides. 2x plus 3 is equal to x plus 1 squared. 2x plus 3 is equal to x squared plus 2x plus 1. Okay, the 2x's will cancel, and then if we bring the 3 to the other side, we get x squared minus 2 is equal to 0. Therefore, x squared is equal to 2. X is equal to plus or minus root 2. However, we know x is greater than or equal to -3 on 2. But x is also greater than or equal to -1. So, for them to be able to intersect, we know that x has to be greater than or equal to -1. So therefore x is equal to root 2. Because we couldn't have, if they're going to intersect, they need to have the same x value and the same y value. Well, here we could have x is less than root 2, but here we can't have less than negative root 2, so that's why it's got to be greater than -1. Okay, so here's where it gets even more complex. For what values of g of x equal g inverse of x have no real solution? So let's let them be equal first. So root 2x plus c minus 1, and we just do let it equal x. Our domain, maximal domain, 2x plus c has to be greater than or equal to 0. So x has to be greater than or equal to negative c on 2. Y has to be greater than or equal to -1. Okay, bring your 1 to the other side and square it. So 2x plus c is equal to x plus 1 squared. I just did 2 steps at once. 2x plus c is equal to x squared plus 2x plus 1. Once again, our 2x's cancel. bring it all to one side, so x squared plus 1 minus c equals 0. Now if we want no real solutions, we know that our discriminant has to be less than 0. So b squared, 0 squared, minus 4 times a, which is 1, times c, which is 1 minus c, has to be less than 0. We get negative 4 plus 4c has to be less than 0. We get 4c has to be less than 4. C has to be less than 1. So if c is less than 1, we have no real solutions. That I mean that they don't intersect. Okay, for what values of c does it have exactly one real solution? Well, we know the discriminant equals 0 when we have one real solution. So the first one will be c is equal to 1, because when the discriminant equals 0, we have one real solution. However, it says find the values and it's worth 2 marks. So then we've got to go, okay, let's have a look at our domain and our range. For the original function, our domain is greater than or equal to negative c on 2. And then f inverse, well, that's going to be our range. Here my range is greater than or equal to, oops, where'd it go? Greater than or equal to negative 1. So here it's got to be greater than or equal to negative 1. Okay, so if c equals 1, like if we have a think about these graphs, if c equals 1, I would get negative a half, negative 1, negative a half, negative 1. If c was to equal 1, my domain would be negative a half, negative 1. It's going to look like that. And then if I put c equals 1 into this one, I would get negative a half, negative 1, negative a half, which would give me a graph. So that's why they, in this case here, they intersect once when c equals 1. Okay, so now let's think about it. What does c do? C's going to move the graph left and right. Okay, so if we, well, it's going to move this graph left and right, and it's going to move this graph up and down. So if we increase c, so if we let c equal 3 on 2, I'm going to get 3 on, I'm going to get, if I put it into here, I will get negative 3/4, negative 3/4, and then if I put 3 on 2 into that, what would my range be? What am I thinking? So if c is 3 on 2, so my graph is going to move my range is still going to be exactly the same. So it's going to be, this time it's going to be negative 3 on 2, negative 1. So it's going to look like that. And then if I graph my inverse graph, that's going to be negative 3 on 2, negative a half, sorry. So that's going to go like that. So we've got 1, 2 intersection points. That's when c equals 3 on 2. What about when c equals 2? So let's get rid of all these graphs. So if c equals 2, we're going to get negative 1, negative 1, negative 1, negative 1, and it's going to look something like that. And I get negative 1, negative 1, it's going to look something like that. So we know this thing here has 2 points of intersection. But then if we made c equal something like 4, if I let c equal 4, okay, we would get negative 2, negative 1, so negative 2, negative 1, and then over here negative 2, negative 1, so that's going to look like that, and that's going to look like that. So you can see there's only 1 point of intersection now. So when c is equal to 2, we know that they still intersect twice, or c is greater than 2. When it equals 2, they have 2 points of intersection, but when it's greater than 2, we have only 1 point of intersection. Root 2x plus c. So that's the answer, but I'll show you. This is a calc-free exam, so it's actually pretty tricky. Root 2x plus c minus 1. So if we do it on here, on my cas, so root 2x plus c minus 1. Okay, so if we bring up c, we can also find the inverse. So what do you have? Root 2x plus c minus 1 equals y. So we would get our inverse is, let me change that to be a y. It is x plus 1 squared minus c on 2. So x plus 1 squared minus c on 2. Now if we sketch both of them, we can say given x is greater than or equal to negative c divided by 2. It doesn't really matter, I don't know why that's not working. Okay, so you can see here, when c equals 3, if this graph here is only going from negative 1, we've got 1 point of intersection. So if I graph the line y equals x, you can see you've got 1 point of intersection. If we change the values of c, so if c gets bigger, we've only got 1 point of intersection. As we get down to 2, you can see that we've got 2 points of intersection, negative 1 and positive 1. If we go to 1, we've only got 1 point of intersection. And if we go to 0, there's no points of intersection. Because we know if c is less than 1, there's no points of intersection. So if I made these go by halves instead of, so here, negative a half, no good. Half, they touch once. 1.5, they touch twice. 2, they touch twice. Anything greater than 2, they only touch once. So in an exam, you would need to know how to get the domain and range and then see what the graph looks like and then see how many times they intersect. I can't think of a way geometrically how to solve, arithmetically, like algebraically how to solve that. So I'd probably do it graphically. But yeah, I'm happy to be corrected if someone can think of a way how to do it non-graphically. All right, so that is inverse functions. Hopefully you understood that. and I'll come back later and teach you about power functions. Don't forget, if you want to sign up for tuition next year in the Berwick, Narre Warren area, wma.com.au. If not, enjoy your Christmas. Bye.